Good afternoon. My name is Jean-Louis Briaud. I'm a distinguished professor at Texas A&M University and the Buchanan Chair in the Zachry Department of Civil and Environmental Engineering. Welcome to the 31st Buchanan Lecture. I started this lecture in 1993 as I had received the Buchanan Professorship, which came with a spendable account. I wanted to share the good fortune I had and thought of organizing a first-class lecture that would honor Spencer Buchanan and allow everyone in the world to be able to attend the lecture free of charge by funding it from the professorship account and video recording it. The Buchanan Lecture has had a remarkable list of speakers, giants in our profession, starting with Ralph Peck. Giants who make the time to come and visit with us and share their knowledge for everyone to enjoy, as they will do again today. Now the program. The Buchanan booklet, including the speaker's PowerPoint slides, is already on the Buchanan Lecture website, and you can access it right now. The QR code is on the wall outside the room. We're also video recording this event, and we'll post a video on the Buchanan website within the next few weeks. We'll also give the video to the Geo-Institute of ASCE for them to upload on their website, along with the other 30 Buchanan Lecture videos already on their site, all the way to Ralph Peck in 1993. Our first speaker will be Dr. Zach Graisley, head of the Zachry Department of Civil and Environmental Engineering at Texas A&M University. He'll say a few words about our department. Our second speaker will be Dr. Ed Kavazanjian with Arizona State University. He will deliver his 2022 Terzaghi lecture on the topic of bio-geoengineering. We'll take time for questions. Our third speaker will be Dr. Marc Ballouz, President of the International Society for Soil Mechanics and Geotechnical Engineering. He will deliver the 2023 Buchanan Lecture on the relationship between theory and practice. We'll also take time for questions. The event will conclude after his lecture, but we'll take a group photo on the stage, so don't go away, before anyone leaves. Then there is a reception at my house. Everyone is invited. Now I'd like to ask Professor Graisley to come and say a few words about our department, some statistics, and looking at our future. Zach?
Well, howdy. Howdy. All right. There's a bunch of UT folks out there, right? Did you all say howdy? You're kind of laughing awkwardly. My name is Zach Graisley, as was mentioned, and I'm the department head for the Zachry Department of Civil and Environmental Engineering. So one quick clarification, the Zachry in our department name is not after me, so just making that clear. Different spelling. So with that out of the way, I'll also mention that I'm going to be very brief because, given this kind of speaking slot here right before our distinguished guest delivers the Buchanan Lecture, is kind of like being a little tiny salad, in front of a steak. And so nobody wants to sit around and eat that salad for a bunch of time. They want that steak to come. So I will be pretty brief. I've been department head for a couple of years. And during that time, it's been an absolute pleasure. We have a great faculty here. Our geotech group in particular is very strong. And many of you are graduate students in that program right now. Maybe even some undergrads out here, I don't know. And so we're very pleased with the direction of the department. We've hired several young faculty recently. We are the largest such department in the country in terms of total number of students and number of faculty. Counting freshmen, we'd be somewhere around the 1,300 and some range in our department, with undergrads and graduate students included. We've got between 75 to 80 faculty, depending on exactly how you're counting them. So we are big, that's for sure, but we also certainly are focused on quality. Our U.S. News rankings just went up by 2 spots. So I believe we're actually, UT and A&M, I think, are tied in undergraduate civil engineering rankings, although I'm pretty sure if you look in the U.S. News, they list us first. So, you know, so it certainly looks like we're in front. So the other thing I would do at this point is I would, you know, do some kind of UT joke, but I can't really do that because my daughter's here now, and she did her bachelor's and master's here at A&M, but she's now a UT student, so I feel really conflicted inside. I don't know what to do, but I'll you know, not do any UT jokes then. The main thing I wanted to say is welcome to all of you. This is an event that the department is very proud of. It has just a very storied history, and you know, Dr. Briaud has been really a model for faculty members in our department in terms of creating a standing in the international community and essentially boldly taking charge and showcasing his particular area of interest, his academic area within civil engineering, and you know, being a leader in his field. When I've traveled to other departments and talked with faculty there, anytime I talk with geotech faculty, they always say, oh, you know, we know Dr. Briaud, he's awesome. And so we're certainly pleased that you've put a good face out there for our department as well. So welcome to all of you. Congratulations to our Buchanan lecturer this year. I'm very much looking forward to it. Thanks, and gig 'em.
Thank you, Dr. Graisley. I want to thank all of you for attending. This is really an awesome crowd, and I appreciate the participation from the University of Texas, from Texas A&M, from other universities across the state, and many practitioners. So thank you for taking the time to come and enjoy this lecture. Now it's my great pleasure to introduce Dr. Ed Kavazanjian. Note that Ed gave the Buchanan Lecture in 2016 and was chosen as the 2022 Terzaghi Lecturer 6 years later. I've known Ed for many years, and I think of him as someone who is very dedicated to his profession, someone with a clear mind, a good sense of what can work, and a relentless quest for what is best for our students. In fact, he recently gave a ton of money to the Geo-Institute to support geotechnical engineering students. Dr. Kavazanjian is a Fulton Professor of Geotechnical Engineering in the Fulton School of Engineering at Arizona State University. He joined ASU in 2004 after 20 years in engineering practice. His expertise includes geotechnical engineering for civil infrastructure systems, design and construction of waste containment systems, geotechnical earthquake engineering, the mechanical properties of solid waste, and the emerging field of bio-geoengineering. He is a past president of the ASCE Geo-Institute. In 2013, he was elected to the National Academy of Engineering, and in 2018, he was elected a distinguished member of ASCE. Among other honors, he received the 2009 Ralph Beck Award, the 2010 Middlebrooks Award, the 2011 Carl Terzaghi Award, and the 2022 Terzaghi Lectureship. The title of his lecture is Bio-mediated Geotechnics for Hazard Mitigation, Environmental Protection, and Infrastructure Construction. Please welcome Dr. Kavazanjian.
Thank you, Jean-Louis. It really is a pleasure to be back here 7 years after I gave the Buchanan Lecture. And just a brief comment before I start my lecture. Everything Jean-Louis said about me, I can say about him. We've known each other for a long time. We've both been leaders in the ASCE Geo-Institute. We don't always agree, but one thing I was always sure of is that what Jean-Louis was doing was, in his mind, what was best for the Geo-Institute, unlike some of our other colleagues. But it's been a great relationship, and it's great to be back here at Texas A&M. So yes, Jean-Louis has already given you the title of my lecture, Bio-mediated Geotechnics for Hazard Mitigation, Environmental Protection, and Infrastructure Construction. And so for those of you who are not familiar with this emerging field in geotechnical engineering, I thought I should start by describing what is bio-mediated geotechnics. And it's one component of an emerging subdiscipline that's referred to as biogeotechnical engineering, and it's a component that addresses processes managed and controlled through biogeochemistry. It's a companion to what we call bio-inspired processes, where we use biological principles to develop new abiotic solutions. And these are really two disparate approaches, but they're linked by a common premise. And that premise is that nature has developed many elegant and efficient biogeotechnical processes through 3.8 billion years of trial and error. You can call it evolution, you can call it intelligent design, but it's really just trial and error where the strong survive and the weak ones perish. So the premise says that we can learn from nature how to use these processes to address a variety of geotechnical problems. So for instance, this is a picture of the Cliff House in San Francisco. It stands on some weakly cemented sandstone slopes. Geologically, yes, they're eroding, but this building and these slopes went through the 1906 San Francisco earthquake without damage. And the weakly cemented sandstone, it's cemented by carbonate by a biogeotechnical process. So how can we learn to emulate that process for our own purposes? Another example on the bio-inspired side, this is a picture of a seed that's germinated and has shot up a stem up in the air, breaking through the soil cover with remarkable efficiency, and has sent roots down into the soil, much more penetrating the soil much more efficiently than any of our probes that we push into the ground, and resists lateral forces much more efficiently than any foundation system that we typically use in practice. So again, what can we learn from this to design better foundation systems, better penetration probes? And then this is a picture of an ant tunnel. Some of you may have had that when you were growing up. I don't know, maybe that's my generation, but they were very popular when I was a kid. You can watch the ants tunnel. And ants tunnel remarkably efficiently, 2 orders of magnitude more efficient in terms of the energy they use to move the earth than our construction equipment, and very safely. The ants somehow can sense what sand grains they can remove without having the tunnel collapse on them. And if they get to a point where they can't, then they back off and they send the tunnel off in another direction. So maybe we could learn to tunnel safer in blocky rock by learning what kind of signals these ants are using to know what sand grains they can remove without having the tunnel collapse on them. So that's an example of biogeotechnical processes that we could use beneficially. Here we're just going to talk about the bio-mediated processes. So what are bio-mediated processes? Well, mediate, the definition from the Oxford Dictionary, is a verb to bring about, and in parentheses they say as a result such as a physiological effect. So we are going to be looking at physiological effects. So a bio-mediated geotechnical process is a biogeochemical reaction that changes the geotechnical behavior of soil or rock that beneficially changes. There are also processes that aren't necessarily beneficial. We're not going to deal with them, or we're only going to worry about them if they affect our projects. But from a geotechnical engineering point of view, from a design point of view, we want to understand and take advantage of these beneficial processes. And these processes may involve a living organism, microbes and fungi, or a biological material like an enzyme. these days, sometimes we take some liberty and we broadly interpret biogeotechnics to include abiotic natural processes, interpreting bio as referring to the biosphere. So for instance, there are geochemical processes we can use to sequester carbon dioxide. And those are natural processes, they're no living organisms, but we would still consider those as a biogeotechnical process, taking the more expansive view that bio refers to the biosphere. So this is a diagram that my colleague Jason DeYoung put together to illustrate bio-mediated processes and how we can use them beneficially. And we have a variety of chemical reactions that can happen in the pores of the soil. We can precipitate inorganic minerals like calcite. We can precipitate organic minerals. We can generate biogas. And all of those processes will affect the mechanical properties of the soil. It can affect the permeability, the stiffness, compressibility, shear strength, volumetric response. And the rate at which that happens is mediated often by biological activity, by microbes in the ground or by enzymes that accelerate reactions. The challenge, we have a pretty good understanding of a lot of these processes in the laboratory. The challenges we're dealing with now, and I'll talk briefly about today, is upscaling. How do we go from laboratory testing that identifies how these processes mediated by biology can affect these properties? How do we go from laboratory columns into the field and deal with inhomogeneity, spatial uniformity, and assure that what we're doing is permanent, or maybe is not permanent if it's an interim solution to a geotechnical problem. So beneficial biomediated geotechnical processes we can identify as mineral precipitation, which can lead to cementation of granular soils, sequestration of contaminants and radionuclides, changes in the densification of the soil, which can be beneficial, and reducing the permeability of the soil if we want to make a barrier. Biogas generation can lead to permeability reduction. The permeability of unsaturated soil is much lower than the permeability of saturated soil, and it can change the undrained behavior. In particular, it can change the liquefaction behavior of the soil, and it can make it much harder to liquefy the soil. So if you can generate biogas in a liquefaction susceptible soil, you can increase its resistance to earthquake loading. We also have biofilms, basically organic precipitation. These can reduce the permeability. They can provide corrosion protection for buried structures. And then on the environmental side, we have transformation of chemical species, which we often take advantage of in soil and groundwater remediation, degrading chlorinated solvents into more benign products like ethene. So mineral precipitation is certainly the most investigated biomediated process by geotechnical engineers. And carbonate precipitation, and more specifically calcium carbonate precipitation, or calcite, is the most studied geotechnical process. There are at least 3 different processes that people are looking at. The most common one is called MICP, microbially induced carbonate precipitation. Some people say calcite precipitation, but there's no guarantee the carbonate's going to precipitate as calcite. It could precipitate in some other forms depending on the environment. That relies on microbes to provide an enzyme that catalyzes this reaction. This reaction, left to its own, would take millions of years to cement soil, but with urease enzyme present, it can cement soil in a matter of days. EICP, enzyme-induced carbonate precipitation, is a cousin to MICP. Instead of using microbes that have the enzyme in their structure, we extract the enzyme from plants or from microbes or from fungi and just use the enzyme directly in the soil. MIDP, microbially induced desaturation and precipitation, is a slightly different geochemical process that both generates biogas, hence the desaturation, and also precipitates calcium carbonate and can then therefore cement soils. These are the 3 processes that geotechnical engineers have focused on in the last decade, a little bit longer for MICP. There are many other mineral precipitation processes. At the center that I direct, we have an investigator looking at precipitating iron to form subsurface barriers. We have a project where we're looking at precipitating phosphorus from agricultural runoff. And of course, salt precipitation is very common. So let's talk about calcium carbonate precipitation though. When I first started working on this, I like to call it geoalchemy. We're turning sand into sandstone by precipitating calcium carbonate. And my first Ph.D. student working on this project identified at least 7 different natural processes by which calcium carbonate precipitates in nature. That leads to things like the White Cliffs of Dover. Those are pure carbonate, well, not pure carbonate, but those are carbonate slopes. It's not cemented sand, it's precipitated carbonate. Again, from a geologic point of view, yes, they're eroding and receding. From a geotechnical point of view, they're very strong and durable slopes. I already talked about the Cliff House in San Francisco. That's more of a geotechnical process. That's a weakly cemented sand where the carbonate has precipitated over years. I actually first got interested in this. I used to do a lot of landfill engineering. In fact, I should have checked the video. I think my Buchanan lecture 7 years ago was probably on landfills and waste containment. But a problem they have in landfills is that the leachate collection system often bioclogs. Well, what's happening? They're precipitating calcium carbonate and cementing the granular material in the drainage system together and clogging it up. And when I first started working on mineral precipitation, my thought was, well, let's learn about that process and let's use that for beneficial purposes. It turns out that process relies on methanogenesis, generating methane. So it's probably not, it wasn't, we decided it wasn't the best process to use for infrastructure projects. So if we can, though, successfully replicate some of the natural processes and get them to occur where we want them to occur, where they're beneficial, beneath a foundation, beneath a roadway, on a slope. The application, there are myriad applications. You know, we can support foundations. We can mitigate fugitive dust, which if you live in the southwest US, you'll recognize as a serious environmental problem. We can mitigate earthquake-induced liquefaction. We can stabilize underground openings in running and flowing sands. We can stabilize subgrades for roadways, slope stabilization, surface water erosion control, scour protection for bridges, making biobricks, making building materials out of aggregates by precipitating carbonate with a much lower carbon footprint than using Portland cement. And there are probably there's certainly more applications than what I have on this list. So, talk about the individual processes. MICP, microbially induced carbonate precipitation, relies upon a chemical process called hydrolysis and urea. And whenever I get to this part of the lecture, I stop and think, you know, I became a geotechnical engineer because I didn't want to take biology and I didn't want to take chemistry. And here I am talking to you about biogeochemistry. But it's a reaction that's catalyzed by urease from microbes. And what happens is if you have urea in the pore water, and you add this enzyme, it will split the urea into a carbonate ion and an ammonium ion. And the carbonate ions are the key. They're in solution. And if we have calcium in solution, and we usually do that but just by dissolving calcium chloride, by dissolving salt into the pore water, the calcium will combine with the carbonate, and boom, you get calcium carbonate. And under the right conditions, environmental conditions, it'll precipitate sometimes in the pores, sometimes on the surface of the particles, preferably for our perspective, at the contacts between particles. There is this issue of the other ion that ureolysis creates, called ammonium. And if we're using calcium chloride as the calcium source, then the chloride has to go somewhere. So the chloride combines with the ammonium, and we get ammonium chloride, which is a salt, and it's a groundwater contaminant. So a lot of the papers on MICP that say MICP is a sustainable process that offers the potential for economic stabilization of slopes, they seem to ignore the concerns about this byproduct. And to truly be sustainable, we need to find ways to better manage the ammonium chloride byproduct. Something that a lot of people seem to ignore. But it is the most popular biomediated process. I did a quick Google search. I've updated this statistic from the PowerPoint slides or the PDF of my PowerPoint presentation. I went back on Google Scholar, and so far in this year alone, there are 2,040 new entries on microbial-induced carbonate precipitation for soil improvement. Think about that. You know, what month is this? This is October, 2,000 new entries this year. Since 2022, over 4,000. So people are paying attention. So MICP, via uriolysis, the microbes can be sourced in two different ways. We have what we call biostimulation, where we stimulate the natural microbes in the ground to preferentially grow the ureolytic microbes. And we have bioaugmentation, where we mix up, we culture the microbes above ground and we inject them into the soil. And initially, most of the work was on bioaugmentation, but people are realizing now that the ureolytic microbes are always there in the subsurface. And you just have to give them an environment and a substrate, a nutrient, that will enable them to grow. And so that seems to be a more sustainable process, if you will, than culturing them above ground, although there are applications like fugitive dust mitigation where you may want to culture them above ground and then spray them on the ground. The initial work on this was back in the late 1990s in Western Australia by a guy named Kucharski. He didn't really divulge what his system was. He called it the calcite in situ precipitation system, and he had a bunch of intellectual property that was pending, and so he never really divulged that it was uriolysis, but it's generally accepted now that that's the process he was using. And notable investigators since that time include Vicky Whiffen, who's in Australia, Leon van Passen, who's now back in the Netherlands. He was at ASU. Carlos Santamarina, Jason de Jong, Brina Montoya, Mike Gomez, Jian Chu, Kenichi Soga. I've stopped adding names to this list because it's hard to keep up with all the people working on this process. What are the advantages of MICP? Well, it's extensively studied. You can see by the large number of papers. People are able to get consistent results in a wide variety of soils, so that's important. And one of the potential benefits is you may be able to reactivate the microbial community once you stimulate it. So you stimulate the microbes, they cause cementation, an earthquake comes along, it breaks the cementation bonds. It's quite possible that all you have to do is add more nutrients to re-stimulate the microbes. Probably need to add a little bit more calcium, but you can renew those bonds, perhaps, that were broken by the earthquake. And I know there are people working on this. What's the disadvantage? Well, one of the big disadvantages is that it takes multiple cycles to strengthen the granular soil to the point where you could consider using it instead of grout or to make a biobrick as a building material. And people don't often talk about this, but sometimes to get like 500 kPa to 1 megapascal strength, it takes 10 to 12 cycles of treatment. And I don't know a lot of ground improvement contractors who want to stick around and go through 10 cycles of treatment. So one thing that we've always pressed in our work, or I've always impressed on my students, is we need to look to get a one and done solution, or maybe a 2 or 3 times and done, but 10 to 12 times is probably not going to be adopted. So it takes multiple cycles. The embodied energy of MICP may be similar to Portland cement. Again, these papers that say that it's a sustainable process don't look at the embodied energy. When you're using urea, you have a very large carbon footprint. Urea comes from natural gas. Now, there are people developing green urea processes, but they're not feasible, or they're not commercially feasible right now. So as long as you're using urea from natural gas, you're going to have a carbon footprint that's very similar to that of Portland cement. And the Portland cement people are constantly reducing their carbon footprint. So it's a little bit of a battle there. I mentioned the ammonium chloride byproduct that can be problematic. The fewer applications you need, the better off you're going to be, because the less byproduct you're going to generate. Fortunately for liquefaction, which is one of the important applications, and for dust control, you don't need a lot of carbonate. You only need 1 or 2% carbonate to strengthen the soil. If you want to make a biobrick, you need to precipitate 8, 10, 12% carbonate. 4 times as much carbonate, 4 times as much ammonium chloride that you have to deal with. And then there are particle size limitations. So these ureolytic microbes are actually kind of chunky. They have a hard time fitting into the pores of a fine sand. So using the microbial process, unless you're going to do like mix and compact, which has limitations, you're limited to, on grain size, to a relatively clean fine sand. Maybe 10 to 15% fines, but any more than that, and the pore side, the pore throats are going to be too small for the microbes to get into the soil structure, unless they're already there. So experience with MICP, lots of lab testing, some centrifuge and large-scale testing, and limited field or field-scale trials. So this is a test that was done at Delft by Leon van Passen and his colleagues. It was a big box filled with soil up to this yellow line. They had 3 injection wells at 1.5 meters spacing. 5 meters across, they had 3 extraction wells. And they wanted to cement a soil mass up to this yellow line here. So this well had perforated pipes over this section. The extraction wells had perforated pipes over the same section, and they used a hydraulic gradient to pull the cementation solution through. They broke down the box, and this was the cemented soil mass that was left. More recently at UC Davis, field scale testing on the UC Davis centrifuge. This is a schematic of a test done by Jason DeYoung and his co-investigators, where they looked at the effect of biocementing discrete blocks of soil. Rather than biocementing the entire block of soil, they looked at biocementing a deep block of soil, a shallow block of soil, and an intermediate depth soil, and how these foundations would respond to those different levels of ground improvement. EICP, the cousin to MICP, using uriolysis, same biochemical process, hydrolysis of urea, catalyzed by the enzyme urease, but it uses free urease. It uses urease extracted from plants or microbes. One thing we learned accidentally is that by adding a little bit of powdered milk to our EICP solution, we were able to get remarkably high strengths at very low carbonate contents. And the mechanism for this is still not understood, but we had read a paper for an investigator looking at dust control where he was adding the dry milk as a stabilizer. He said it stabilized the enzyme. So we thought that sounded good, let's stabilize the enzyme. And incidentally, we found out we were getting 4 or 5 times more strength by including this additive. So this is a plot of the unconfined compression strength of a laboratory column versus the calcium carbonate content. And out here, this is all MICP data from multiple cycles of treatment, 8, 10, 12 cycles of treatment, getting a megapascal or more strength. Some more recent work done by Jason DeYoung and Mike Gomez, these green triangles represent some success they've had in the laboratory, again, with multiple cycles of treatment. These red triangles here are our results for biocementing Ottawa sand, Ottawa 2030 sand, our standard laboratory sand, with 1 cycle of treatment and less than 1% carbonate. And we're getting strengths up to 2 megapascal, which is more than enough for supporting foundations and creating biobricks. Why do we get that hard strength? We've been working on that problem for about 5 years. You know, maybe it's because I'm getting more gray hair. People keep asking me when I'm going to retire. And my answer is when we figure this out, maybe then I'll retire. So EICP advantages and disadvantages. The advantage, less substrate, lower cost for the raw materials, and maybe if we can get that high strength in 1 cycle of treatment, 1 and done. We only have to pump the chemicals into the ground once and we can walk away. Because we have less carbonate, we have less ammonium chloride. It's a little bit more efficient too, so all the carbon in our treatment solutions goes to forming calcium carbonate. In MICP, some of the carbon goes to feeding the microbes. So we're more efficient chemically. And the enzyme, the basic enzyme unit is much smaller than the microbe, so it can penetrate finer grained soils. Now, it's still somewhat limited by permeability. Right? If you have a low permeability soil, it's hard to get the solution in there, but at least it won't be blocked by the pore size. So a typical enzyme unit is like 12 nanometers, 1/10 the size of a microbe. What's the disadvantage? Well, Inconsistent biocementation. So we had this wonderful result with Ottawa 2030 sand. We got 1.5 to 2 megapascals, one cycle of treatment. Then we ran out of Ottawa sand, so we bought another batch from one of the online sources that sells Ottawa 2030 sand. And we treated it, and we only got 500 kPa. Boy, what's going on? We bought a third batch of sand. We treated it, Ottawa 2030 sand, all from the same formation in the Midwest US, the St. James Formation, 99.8% silica dioxide, rounded to sub-rounded particles, and the third batch, we got 200 kPa. So we're getting an order of magnitude difference between what we call the B1 sand, which looked like this, and the B3 sand, which looked like this. And then we had an intermediate sand. We now have 7 different kinds of Ottawa 2030 sand from quarries across the country. And all of them, we have kind of a hierarchy of the high strength to the low strength, and we're trying to understand why we get that high strength, and then if we can figure that out, how we can treat all sands so we can get that kind of high strength out of any sand using our process. And then I can retire. Yeah. So the disadvantage, inconsistent biocementation, the mechanism isn't well understood. Another problem is the enzyme reaction is really fast. So if you're pumping things through a well, you get they call bioclogging. Right around the well, a lot of calcite precipitates and it clogs up the well, and then it gets harder to put more substrate and more chemicals into the ground. And the MICP process, you can slow down. You can slow down the ICP a little bit too, and we're working on that. All right, experience with the EICP. Lab data is starting to accumulate, more and more people. Several investigators are studying ways to slow down the reaction. You can change the pH of the poor water. You can chill the EICP solution. That slows down the reaction. There are some studies using fine-grained soils and maintain that they've improved clay soils using EICP. And it's always mix and compact, because otherwise you can't get the chemicals into the soil. And the problem is, the papers that I've reviewed, they don't do a control. So part of the EICP solution is salt, calcium chloride. If you just mix calcium chloride with clay soil, you're going to suppress the double layer, and you're going to make it swell less, you're going to make it stronger, you're going to make it stiffer. And I've rejected manuscripts that I've been asked to review saying you need to do a control, and for some reason those manuscripts never come back with a control in them. The work just seems to disappear. So I'm a real skeptic on using it fine-grained soils. These processes, carbonate precipitation processes, are for granular soils. Wind tunnel testing and field trials of fugitive dust control are underway. We were fortunate at ASU, we have our Earth Sciences department has a big part of the Mars missions for NASA, and so they built a special wind tunnel for studying dust storms on Mars. And we had access to that, and so this tunnel creates a perfectly laminar, or almost perfectly laminar flow, so we can run that over our sample, gradually increase the speed, and measure what we call the threshold detachment velocity, the wind velocity at which the soil particles start to detach and erode, and then become entrained in the airflow. So we've done some extensive testing with the wind tunnel, and so typically we'll test bare soil to get the dry soil to get kind of a baseline. We'll wet it. So in practice, the standard practice for controlling fugitive dust on a construction site, for instance, is to wet it. They got a guy out there with a hose who stands there 24 hours a day spraying a stockpile. Or if it's a larger site, a land development site, they have a water truck that starts at 8 in the morning and goes till 6 in the afternoon, keeping the soil wet. Sometimes it works. In Phoenix, it's 110 degrees, 20% relative humidity. The truck drives away, the soil dries out, you still get dust, but you don't get fined because it's the best available technology. So you're complying with the environmental regulations. Well, if we could spray our carbonate crust on once, and if it's going to be durable, think of all the savings in terms of water consumption, in terms of vehicle fuel, in terms of the emissions generated. So we've been really focusing on fugitive dust as one of the applications. And so in the wind tunnel, we have the bare soil, we have the wetted soil that gives us a detachment velocity. We have a control where we just use the salt solution. So in the mining industry, the dust palliative is magnesium chloride typically. Then we have our EICP solutions, and in this case we had 2 different concentrations, 2 molar, 1 molar, and we maxed out the wind tunnel. We couldn't get a high enough velocity in the wind tunnel to cause erosion. In addition to fugitive dust, we've been looking at EICP to support foundations, to make columns in the same way you would make a soil cement column. So fugitive dust control, worldwide air quality problem, primarily due to windblown soil. It's not industrial emissions, it's soil. It plagues many arid and semi-arid areas around the world, the southwest US, eastern China, North Africa. But in fact, now we're getting interest in more temperate climates. So for instance, we're doing some testing for an iron ore mine in Minnesota. They have a problem with the spring thaw. When the ground freezes in the winter, the ice expands and disaggregates the soil. When it dries out in the spring and the wind blows, they get dust storms. So we're doing freeze-thaw testing right now to see what the durability of our process is with freeze and thaw. And when the Maine Department of Transportation found out we were doing that, they said, oh, we have the same problem with our unpaved roads, our low-volume roads. So there are lots of, every time we turn around, there's more interest in this. As I mentioned, best available technology, spraying water or using salt. But the mining people can use salt. If you're in a civil infrastructure project, environmental regulations would prevent you from using salt typically. Google Scholar citations, not the 2,000 we saw for MICP, but for EICP for dust control, 140 so far this year. So there's growing interest and attention to this particular process. So the concept is to create a wind erosion resistant carbonate crust using a sprayed on EICP solution. The advantage is it's one and done. The disadvantage is that it costs more than just spraying water, and this potential environmental impact from the ammonium chloride. So we have several test sections. We have one where we're collaborating with 3 industry partners, 2 landfill owners and 1 mining company that we deployed in the Phoenix area. And my Ph.D. student will be defending her thesis on that on Thursday, next week. So stay tuned. We spray on the EICP, and this goes to the speed of the reaction. The first time we tried to do it, we put everything into a tank and we started spraying the mixture, and before it got out of the nozzle, it precipitated and it clogged the nozzle. So now we spray the 2 solutions sequentially. We tried mixing them at the nozzle, that got complicated. So now we just have 2 component solutions. We did try mixing at the nozzle, but now we're spraying them on sequentially. First field trial in 2021 in Arizona landfill, so they're my students spraying their EICP. One thing we learned, so when I lived in the Bay Area, there was a news broadcaster who used to say, if you don't like the news, go out and make some of your own. Well, we treated these dust control sections, and then we waited for a dust storm, and there wasn't one. And, you know, my students want to graduate. They want to get out in the field. I understand that. So we created our own dust storm. We started dragging a piece of chain link fence behind a pickup truck, going back and forth over our sections and measuring the dust control and demonstrating that the EICP was superior to, well, superior to nothing, superior to water, and equivalent to the salt treatments that we used. So we had this field work. We had 4 test plots. We had one with our EICP solution. We had one untreated, so a baseline plot. One where we mixed the EICP solution with some xanthan gum. We call that XEICP. One where we used magnesium chloride. And we also did one with MICP, just to be fair. We don't want to be biased. And again, that work is just about done, and Miriam will be presenting her dissertation next week, defending it. The other application we've been looking at is making biocemented columns. So the concept, create a column of biocemented sand for ground improvement, the same way you would use grout to make a soil cement column. And this goes back, so soil improvement by making columns is widely used for a variety of processes in our industry, right? So we can use it to support residential foundations, embankments, retaining walls. This is from federal highways on concept of installing lattice cellular configuration. I like to show this slide because, one, we can do this with biocement. We can install a perforated pipe and biocement the soil in the same way this fellow is using soil nails. But more, so this was a figure from a 1985 by Jim Mitchell and Billy Villay based on work done by a guy named Lizzi in Italy in 1960. And he came up with this idea of stabilizing slopes with soil nails by knitting it together, but he didn't call them soil nails, he called them root piles, pale radice. And to my mind, this was the first bio-inspired concept. This was using a biological principle, trying to recreate the way root systems stabilize soils abiotically. So we have a test pit at ASU. It's 12 feet deep, 20 by 8, and we were able to install 7 1.5 to 3 foot diameter soil cement columns. We filled it full of sand, local quarry sand. We used the conventional grouting approach, what we call tuba machette. So we have a perforated pipe, and we use a packer, and we inject over a discrete interval, about a 1 foot interval, starting at the bottom and working up to the top. We use 3 cycles of treatment, not one and done, 3 times and done, but at a 24-hour interval, so it was 3 days to treat it. We designed it to get 500 kPa strength, and so the grouting manuals and all say, if you're going to do soil cement, that's a minimum strength that you want. So we designed our system to get that minimum strength. So this is our crew down in the bottom of the pit, working in a hot summer heat, but with long sleeve shirts, well, mostly long sleeve shirts, as required by our health and safety program. And here we've created the columns, and we're excavating down and making measurements, geophysical measurements, taking samples for carbonate content and for shear wave velocity measurements. This is after we're done. And we've exposed one of the columns. Now Miriam's a tall girl, she's like 6'2", so this is like a 7-foot column here. You can see the biocemented column that we created using EICP. One more carbonate precipitation process. Microbially induced desaturation and precipitation. These days, though, we forget about the precipitation. We found out we didn't need it. That to mitigate liquefaction, which is our goal, all we need to do is desaturate the soil. So it's an alternative carbonate precipitation process. It has more benign byproduct. The benign byproduct is nitrogen. That's why we started using it. So it desaturates the soil by generating biogas, and that biogas is non-toxic nitrogen. Basically, it's a process called denitrification. The nitrate is reduced to nitrogen and carbon dioxide. The carbon dioxide goes into solution, and that gives us carbonate ions if we want to precipitate. But these days, we ignore the precipitation, and we just focus on the desaturation due to the nitrogen. So advantages of this: one, the denitrifying bacteria everywhere. And our wastewater treatment colleagues are very familiar with this. It's a standard wastewater treatment process, denitrification. The carbon dioxide gets those carbonate ions. Nitrogen is pretty insoluble, so it creates bubbles in the pore that are very durable, long-lasting, decades, we now believe. And so the carbonate precipitation is slow. So when we started this, the first time we did this, we were very disappointed because it was taking 6 months to a year to precipitate as much carbonate as we could precipitate with EICP or MICP in a day or two. But then we realized, well, heck, but we've desaturated the soil from the get-go, and desaturation is a liquefaction mitigation mechanism, so let's focus on that. So here's some test data. This is the cyclic resistance ratio, cyclic shear strength of the soil. This is the number of cycles causing the soil to liquefy. This is the cyclic strength curve for the unimproved soil. With just 0.4% carbonate, we had a 50% increase in the cyclic strength. With 0.9% carbonate, we doubled the cyclic strength. So the benefit of, if we're going to use the precipitation, if we need it, is that we don't have to precipitate a lot of carbonate. But if we look at the desaturation, come on, Ed. This is the fully saturated cyclic strength curve. This is with 1% desaturation. This is with 3% desaturation, with a relative density of 75% soil. So with just 3%, we've increased the cyclic strength 50%. Typically, we can get down to 90% as a degree of saturation, 85 to 90%. So advantage of MIDP, the denitrification process is well studied and well understood. Desaturation mitigates liquefaction. there's a benign byproduct unless there's sulfate in the ground, in which case you get hydrogen sulfide, which isn't good. So you probably wouldn't be able to use it there. But the precipitation, too, is very efficient. And the reason for that is illustrated by this scanning electron microscope photograph from my student Sean O'Donnell. This is an Ottawa sand particle. This is an Ottawa sand particle. These are calcite crystals that have been forced into the contact zone between the particles by a bubble. That's the remnant of a bubble. That's organic matter that gathered around the outside of a bubble that grew in the pores and pushed the carbonate crystals into the contact zone, making it a very efficient way to biocement soil. Now, the downside is those bubbles also reduce the permeability of the soil. So there's a trade-off there. But within a day or two, we can usually get enough desaturation to mitigate liquefaction. So disadvantages: precipitation very slow. The longevity of desaturation is unproven, but we're getting more and more data now that shows that it's long-lasting. The gas may coalesce in lenses and vent. If you try and generate too much gas, you create a lens and it vents up to the surface. The potential for hydrogen sulfide, if sulfate is present, and the nitrogen gas will slow down the permeability. So if you want to get precipitation, that's why it takes so long to precipitate carbonate, because the bubbles really slow down the permeability of the soil. So we've done some centrifuge testing at UC Davis on their small centrifuge. This is the model. We had 3 elevations where we had sensors. We spun the model up. Well, we desaturated the soil under 1 G, and then we spun the model up to about 50 Gs and maintained a good level of desaturation, about 80%. Then we shook the soil. We shook the model with 10 cycles or 9 cycles of loading, and we had some desaturation or some resaturation up to about 90%, but then overnight it dropped back down again. And then we let it sit overnight, and then we shook it again. And so if the soil was untreated, it would have liquefied in this first shake at a 0.04 G target amplitude. The first day we had 9 shakes up to 0.4 G. We managed to get a pore pressure ratio up to about 0.75, but that's not liquefaction. Overnight it dropped. The first shake the next day, we did have liquefaction in the top layer, and we think that's because of gas that vented overnight when we spun it down. But then once that gas dissipated, we had very little pore pressure generation for the rest of the model test. Now we've done field testing, so we collaborated with Portland State University, Dr. Stokey, who's out there somewhere, and the Oregon Division of Oil, Gas, and Mineral Industries, with funding from the NERI program at NSF, and we desaturated 2 sites in the Port of Portland. So Portland is a high seismic zone threatened by the big magnitude 9 earthquakes in the Cascadia subduction zone off the Pacific Northwest coast. And so in a magnitude 7.5 earthquake, the soil in the Port of Portland probably wouldn't liquefy. But in a magnitude 9 earthquake, you're talking about many more cycles of shaking. These soils are expected to liquefy. These are silty sands. And 90% of the fossil fuel resources for Portland come in through the port. So the port was very concerned about liquefaction, and they allowed us to do test sections in 2 areas, one right by the airport and one in the port that they called their critical energy infrastructure hub, where they had all their storage tanks. And we were able to successfully desaturate the low plasticity silt layer, reducing the P-wave velocity from the P-wave velocity of saturated soil, 1,500 meters per second, to a lower number that's indicative of desaturation. And it's been 3 years now, and we haven't seen any change in the desaturation. So good evidence that 1, we can desaturate finer grained soils, and 2, that the desaturation has longevity. We looked at the economics of this. So we did what cost analysis, fancy name, techno-economic analysis. And we worked with the ground improvement contractor, Condon Johnson. We took a site in the Port of Portland, and we assumed clean sand simply because we wanted to be amenable to a conventional ground improvement technology. You know, a lot of times if you have liquefiable soil under existing infrastructure, there's no cost-effective way to remediate it. If it has too much fines in it, you can't grout it, you can't do densification, and you're really stuck. So we assumed we had clean sand so that we had an option, which was grouting. And we developed this in collaboration with the ground improvement contractor. They developed the grouting system. We developed our bio system. Then we had them do the cost analysis for us. And we were about 1/3 the cost of grouting to stabilize that foundation. So that's carbonate precipitation. Precipitation of other minerals and metalloids. Phosphorus is of a lot of interest in agricultural communities. Phosphorus and nitrogen in agricultural runoff is a big problem. We built a system to precipitate the phosphorus and then discharge into a wetland when denitrification would take care of the denitrification. We use steel slag, which is a very high pH material, to precipitate the carbonate. This was our field test. Again, this is one instance where it precipitated too fast. The slag has a really high pH, like 12, and by the time the agricultural runoff, which we collected from tile drains in the field, got through this slag pile, all the phosphorus had precipitated out and it clogged the drainage system. So we need to learn a way to slow that down. Other precipitates, iron, salt. You can co-precipitate strontium with carbonate strontium carbonate. And we have projects on precipitating selenium as selenite, arsenic as arsenite, and chromium as chromate using biogeotechnical processes. What are the challenges with mineral precipitation? Well, one is the fines content. Not only does it slow down the permeability, slow down the movement of your substrates because of the permeability, but if you're going to biocement soil, you got to cement all the particle contacts. The number of particle contacts goes up with the square of the particle diameter. So as the particle gets finer, you need more and more carbonate to stabilize that. And we see that when we compare coarse sand to fine sand. When we get into silts, the number of contacts you're going to have to precipitate is unfeasible. And then the permeability that affects the substrate. We get the bioclogging due to mineral precipitation. We get organic matter growth, which can also clog up the system. We get loss of permeability due to gas generation. If we're precipitating carbonate in like a permeable reactive barrier, we saturate the media. We don't know what the permeability is, the permanence is of a lot of these processes, and we have the process of byproduct management. So anytime we look at a precipitation process, we have to deal with these issues. Transformation of organic chemicals, it's perhaps the most advanced biogeotechnical process because our environmental colleagues have been doing this for years. Process of interest include aerobic and anaerobic degradation. We take advantage of that in our landfills. Denitrification and uriolysis are both chemical transformation processes. Importantly, reductive dechlorination, taking chlorinated solvents and reducing it to ethane. And we have a couple of test sections dealing with enhancements to this technology. Sustainability. So there seems to be an assumption out there that just because it's bio-mediated, it's sustainable. And I think I alluded to that earlier, or environmentally friendly. And that's not true. You need the proof is in the pudding. You need to do a sustainability analysis. As I mentioned, the embodied energy in urea that we would use for biocementation is very similar to what we have in Portland cement. The carbon footprint is very similar to Portland cement. So you can't say just because it's a bioprocess, it's going to be more sustainable. So in our center, we've developed life cycle sustainability analyses that consider the technical issues like cost and permanence, energy consumption, environmental impacts, and all the technologies we develop in the center, we subject to a life cycle sustainability analysis to either demonstrate that they're more sustainable or identify how we need to change our processes to make them more sustainable. We have a publication that illustrates this on life cycle sustainability assessment of EICP for fugitive dust control, and we learned two things from this assessment. One was if the EICP crust lasts for more than 2 weeks, and we're pretty confident it will unless you start disturbing it, it's going to be cheaper than running a water truck twice a day. Two, the environmental impacts are going to be less because we're going to consume less fuel, generate less emissions. The downside is we need to worry about this ammonium chloride byproduct, and so we have people, I have a student now working on a fate and transport analyses to see under what conditions this byproduct is going to be a problem. And in fact, ammonium chloride is a fertilizer. So if you can vegetate the site, which isn't that easy in Arizona, you may be able to consume the ammonium chloride. This is an example of some of the outputs from our sustainability analysis. This is EICP, this is water, so you can see EICP is favorable for water consumption, primary energy, global warming potential, project cost, the social cost of carbon. Where we lose is the acidification potential due to the ammonium chloride. So as a decision maker, you'd have to decide if it was worth it, at least at this point. I think a couple of times I've alluded to the center, so I need to give credit to my colleagues at our Center for Bio-mediated and Bio-inspired Geotechnics, supported by the NSF. We're in a 9th year of a 10-year funding period. It's ASU, Georgia Tech, New Mexico State, and UC Davis. In addition to our technical programs, we have education and outreach programs to K through 12 and the public, and an industry partner program. And our industry partners contribute to our research. So this is just a snapshot of the 20 industry partners that we currently have working for the center. We have owners, contractors, consulting firms, and regulatory agencies. So we say we have the full value chain of the entities that are involved in our work. And just a little word, I don't know, I guess this is more my generation, but people sometimes get us confused with CBGB, right? CBGB was the penultimate punk rock club in New York City, Blondies, the Ramones, the Talking Heads. Well, we're not CBBG, we're CBBG. So CBGB was the home of underground rock. We're the home of underground microbes. All right, so with biogeotechnical future, I think we've only scratched the surface. We've only looked at a few processes and methods to date, and I think there's opportunities to do much more. And that concludes my presentation. Thank you for listening.
Thank you, Dr. Kavazanjian.
My pleasure.
I have two things for you. I have a certificate.
All right, thank you.
Signed by our department head and myself. And I have a copy of my 2nd edition book that I'm giving to you. There's a chapter in there that has 22 case histories. And I'm hoping that this will help students get more interested in geotechnical engineering. Tower Pisa, of course, Eiffel Tower, Three Gorges Dam, Teton Dam, a lot of case history. So I hope you enjoy it.
Well, thank you very much.
Thank you so much.
I will display it proudly on my shelf with my other books. Just quick story, when I moved into a new office and they showed me the office plan, I said to the office planner, where are the bookshelves? She said, oh, most faculty members these days don't want bookshelves. I said, no, I need as many bookshelves as you could fit into this office. So I'll display this proudly. Thank you so much.
Thank you. Now it's my pleasure to introduce Dr. Marc Ballouz. I've known Dr. Ballouz since 1988, when he first came to my office on campus for his graduate degree. Fast forward 35 years, and Marc is now a remarkable international geoengineering leader. What makes Dr. Ballouz stand apart is his ability to multitask at high speed. I typically meet with each one of my graduate students once a week for an hour. Marc would come every week with an impressive amount of new work accomplished during that week, and always looked like he was coming from the beach. He's as comfortable with the differential equation as he is driving a bulldozer, and he does. He's as comfortable with computer programming as he is with a wrench in his hand. He's also a very generous person, including a major gift to the International Society Foundation to help disadvantaged geoengineers worldwide. Add to this that he's a tremendous social talent, and you will understand why he has been very successful in climbing our international professional ladder. Indeed, he became president of ISSMGE in 2022 after the stiffest competition that our international society has ever seen. There were 5 candidates, and Marc came on top after a series of 4 consecutive votes. His degrees include a bachelor degree from the American University of Beirut in Lebanon, a master and a Ph.D. from Texas A&M University. After graduation, he started his own geoengineering consulting and construction company, which grew with offices in several countries. As CEO, he traveled extensively, but never lost his appetite for fast cars and daredevil skiing. It's amazing that he's still alive. More than 10 years ago, he moved to Austin, Texas, which is one of his resting places when he's not on the road. He's received a number of awards and recognition, but one that is impressive and caught my mind is the 2017 medal from the Sheriff and Fire Department of Harris County for his help to Houston citizens stranded in Hurricane Harvey. When he heard about the devastation, he jumped in his truck with a small boat in tow and drove from Austin to Houston, where he rescued a good number of people. We're delighted to have Dr. Ballouz with us today to deliver the 2023 Buchanan Lecture on the topic of geotechnical engineering, marriage between theory and practice. Please welcome Dr. Ballouz.
Wow. I didn't know you were going to talk about those details, but I don't know how to start. I've lectured all around the world, but this time it's a bit emotional. Seeing classmates, it's tough on me. After so many years, Tot Svoboda, Krishna, my dear friends, Adele, Philippe Jean-Jean, it's amazing. Anwar, wow. And I didn't come here to give a technical lecture. You cannot give a technical lecture in the presence of geolegends like Jean-Louis, Ed, Ken Stokey. I'm so happy you are all here, coming from different cities, different places. Jorge you surprised me. From Austin, UT students. I have the same problem with Zach because my son is a Longhorn and I'm an Aggie. But I have to say to all the Aggies, Gigam Ags, thank you for being here. I don't know if they have any students from Texas State University. Anybody from? Yes! These are my students from last year. Thank you all for coming. I don't want to forget the one who traveled from far and is my student from Lebanon. Ghassan Akrouche, are you here? Yes. You graduated 10 years ago and you are following my footsteps, and I think you are one of those students who bypassed the teacher. And thank you for coming all the way from Florida. Jerome is another student of mine. You're doing a great job, soon to be a doctor at Aggieland. Congratulations. I didn't forget you taking a video. She's the one who traveled from across the globe, from Lebanon, my fiancée, to be at this lecture. I'm surprised you're not sleeping, jet-lagged. You arrived yesterday. So I hope you'll enjoy this lecture. I will start by showing you a picture of when I was a student here. I didn't change, right? Grad school, 1988. This for sure it didn't change. Me and Dr. Briaud in the Waxahachie tunneling project, doing a pressure meter test, 220 feet underground. I like this picture. GigaMAGS. And of course, it's an honor to be, after 31 years, a lecturer. How it started with the first lecturer, Peck. I was the one distributing the pamphlets as a student, preparing the overhead projector. And he insisted at the time to sit with the students, and we took a picture. Not a selfie, because there was no cell phone at the time. So it's fuzzy. So I will start my lecture. I have 4 chapters, but the first one that doesn't have a number, because I'm the president of ISSMGE, I have to tell you a little bit what is ISSMGE. So ISSMGE, International Society for Soil Mechanics and Geotechnical Engineering, is the oldest and largest society representing our profession worldwide. It was founded in 1936 by the father of modern geotechnics, Carl Terzaghi, on the portrait here. And nowadays, it comprises of 90 national society of 90 country members. And the structure, you can find it on the website. You have at the top the council, which are the 90 countries, and then the board comprised of 12 board members, and recently we chose a new secretary general. So you have the president, 6 VPs representing 6 continents, appointed board members, and immediate past president. But the really working force are the board level committees, that one of them is headed by Professor Marcelo Sanchez, doing a great and very difficult job overseeing the technical committees. I don't know if he was able to come. Marcelo is here. He was busy. He told me he's going to be busy, but hopefully he can join us later. This is a picture of the board. You can recognize them from the pin. And this is the most recent one, when the previous Secretary General left service after 24 years, and he received the Medal of Lifetime Achievement. This was in Astana, Kazakhstan, a month ago. And this is the new Secretary General, Professor McNamara. The technical committees, the real working technical force, we have about 40 technical committees, and I hope you are part of them. I think some of you are, and I encourage you to join through your national society. But for the young engineers, like Professor Briaud was saying, I encourage you to apply to the foundation so you can get help to go attend conferences at international levels. Also, don't forget the awards. If you have a good paper research, check with the organizing committee of the conferences happening and apply, or push them to apply to become a Bright Spark lecturer, such as this certificate. You will get a certificate. And so far, I gave about 24 certificates in 1 year as new president. And the new Lifetime Achievement Medal is the other side. Instead of the young, we are looking also at the old renowned Lifetime Achievement engineers. On the ISSMGE website, you can see the coming list of events, starting here at the top. Maybe it's missing the Buchanan Lecture. And at the bottom is in 2026, the conference, international conference in Vienna, and this is where I will no longer become president. And all these in between, please look at the website and try to go international. Don't forget, all of you, especially the young, to look at our virtual university. It's a series of hundreds of videos, lectures, webinars, all open access and organized in groups. Also the International Journal for Case Histories, hundreds of papers, high-quality papers, and thousands of papers in proceedings, all open access for free. It's really impressive and very important for the students doing research. And don't forget to open an account with GeoWorld. GeoWorld is our geotechnical Facebook, if you want. It's a very nice platform. The most feature that I like is GeoMap. I discovered with this interactive map that I have a neighbor who is a geotech engineer. What's new achieved last year as president? If you look at the website, you can see we launched a series, so far 11 talks, interactive technical talk, bringing together people from industry, academia, young and renowned from different parts of the world, geographical diversity, and to discuss one subject. So we're trying to cover all 40 technical committee subjects. And the new idea zone, if you have an idea, you can share it easily with us. And if we like it, we'll implement it so that we don't have to think too much. We're exchanging websites. So if you go on any National Society website, you can connect to us and vice versa. This is something we launched new. Another baby project I'm launching is Geoengineers Without Borders. And this comes from my feeling of helping. It's like at the image of Médecins Sans Frontières. If there is a disaster or geohazard failure somewhere in a country, any country, we go from this team is ready to go help with the reconnaissance, just be supportive to other fellow geotechnical engineers worldwide. Also list of events, we introduced the interactive map. So instead of looking at the calendar, you can also look at the geography. If it's in your continent, you can go to this event, and many more. The most important is launching the new Lifetime Achievement Medal. And the 2023 winners, the first one was Professor Mike Yamlukowski, who is friends with many in this room. Unfortunately, Michele passed away one day before he knew that he is a winner. And I had to give the medal 2 months ago to his daughter. He was amazing. Anywhere I go around the world, people loved him and appreciated his work. And we will miss him so much. The second winner was Harry Poulos, and more winners to come, 2 medals every year. Exceptionally this year, an extra medal was given to the Secretary General who served ISSMGE for 24 years. So Professor Neil Taylor got a Lifetime Achievement Medal. It was a big surprise for him in Astana. Finally, I shouldn't forget the corporate associates. These are the companies. So if you are working in a company, please try to join your international company, your international family by being one of the members here. And I have a video, I don't know if we have time to launch it, explaining why you should join. If we have time, actually, we created 2 videos, one for the national member societies and the other for the corporate associates. My activities as president, in summary, I don't know if you can read at the bottom, but in 1.5 years, I toured the world physically twice and visited more than 26 countries with 104 events attending and being part of online or, in person. It's too quiet. Finally, my lecture. Maybe we'll launch the video at the end if we have time. The lecture, as I said, so we have 4 chapters. The first chapter, marriage philosophy, I will tell you general. So as I said, I'm not here to give a technical lecture, but more to tell you what not to do from my mistakes in your professional life. I will start with the units, the crazy units. Crazy because in some countries they use SI system, in other metric. In the US, I don't know if you're still teaching in feet and pounds, but it's so confusing and it's so dangerous. So every time you're doing a solution, please go through the scrutiny of checking compatibility of units and the logic of your answer. This is so important. You cannot believe how important it is. 10 milliliters of antibiotics can save your child's life. These are my children, long time ago. I'm still young here. But 10 liters can really kill an elephant. Just one letter, we removed the M. Another crazy story, outside geotech, but still important. I was having dinner with a friend, and he was telling me the story of his cousin who developed the orbiter to take pictures on Mars, the first one. And he told me that it collapsed, it disappeared. And then he said because of the difference in unit between his French team and the American team. I didn't believe him, so I looked it up, and it was right there on the internet. The software calculated the force of the thrusters needed to exert in pounds of force. A separate piece of thrust took the data, assuming it was in metric newtons. So this is not a joke. Another thing I like to tell you to be careful about is intuition. I used to do this mistake of showing that I know, and then you get a question on the field or on site, and by intuition you give the first answer, and it's always wrong. Always wait, collect the data. For example, if we take a rope from here and throw it all around the earth, and grab it from the other side, make it tight, and then you take the same rope, make it 6 meters longer, so the green rope is 6 meters longer than the red rope. How high will it rise above the ground? The first intuitive answer is negligible, right? But if you do the simplest math we learn in school, elementary school maybe, you will discover that it will rise 1 meter. And it's independent of the initial radius, so it can be a soccer ball. I don't know if Philippe brought with him a soccer ball. Did you bring a soccer? He was. By the way, Central Park is still open. I checked this morning. We can go after this lecture. So whether it's a ball or the earth, 6 meters more will make the rope rise 1 meter extra. Another nice exercise, if you take a piece of paper, maybe this one, and you start folding it 1 time, 2 times, 50 times. So if you fold it 50 times, how thick will it be? 10 centimeters, 1 meter, 10 meters, or will it reach the moon? Intuition may be 10 centimeters, but if you do the math, the simplest math, again, I'm telling you, simplify the problem, no matter how complicated it is. Simplify just to get the feel of the order of magnitude. You will see that it's about 140 million miles. And if you compare, it's the average distance between the Earth and Mars. So by folding a paper 50 times, you can reach not the moon, but Mars. Third part of the first chapter is something I introduced to myself, and I like to share it with you, is SOLGE. I keep saying SOLGE all the time. Every time somebody asks me a problem or a question, I say, wait, let me collect soil, at least soil, load, geometry, so I call the architect, get all the drawings, and the history. I check, have you had a failure before in this area? How deep did the neighbor go? What did he use as, just to get a feel, is there any water source nearby? And sometimes it's the most important part is the history. And always, always visit the site, especially if it's a forensic case, which is my expertise, to solve a failure or a problem. And then you start thinking, and I will tell you what I mean by that. So what is the mode of failure? What are the forces? What is the applicable theory? Which software would apply? And then you put together all these and you put at the top safety and then cost and functionality, and then this is where the problem starts getting solved in your head, not on the computer at the beginning. You know, anybody can, like if you bring a superintendent that experience, he can build a project, but it may cost double or it can collapse. So that's the difference between us and practitioners who do not have a degree, is we can put it all together safely. So what I'm suggesting is sophisticated thinking prior to sophisticated 3D analysis or whatever. And use as much data as possible and as many methods as possible and as available before you judge. So like you can use 3D visualization and holograms, technologies such as drone mapping, 3D finite elements, of course, and then you give the solution. Final part of the first chapter is engineering life. I will go back to the basics. So if you take the simplest problem of walking on sand and solve again, so soil, load, geometry, and history, you look here. It's showing that the lady is leaving a settlement bigger than the man who has more load. So that's proof that settlement is related to stress, not load. And if you keep going with the simplest equation of Carl Terzaghi, simplest form, which I think Briaud does not agree with let's keep it here. So just for fun, simplify it, and you will see that the ultimate capacity, if you use Terzaghi, is actually less than the applied stress. So is this failure? I mean, you can walk on sand without failing. The footing on sand will in reality sink, but then will stop, which is not the case in clay. So let's keep thinking more, and then why are they not sinking too much? Because they're smart and they're walking, and you do this the same on wet sand. So when you walk on wet sand, you have the apparent cohesion or the suction helping you with this wetness. And if you put that into the equation, you'll see the difference. Now you have stability, and look at the effect of the large suction effect in the first term. So what now, another question, and I'm coming to tell you that a simple theory can be approached from different angle. What if we take the same equation and ask you, what's the settlement if they walk on the dry part of the sand? You can put the settlement as an unknown and then, bring this quantity of settlement is 5 centimeters, which makes sense. So why am I telling you all this? No matter how complicated the problem is, simplify it first, get a feel, and then move on with more sophisticated analysis. If we talk about deep foundations now, and you bury yourself up to the knees, so the pile length up to the knees from here down is like 0.5 meter or 0.6 meters. Pile perimeter, 0.3 meters. The question is, what's the force needed to save you? Again, intuition may be same as your own weight plus a little bit more. And here I want to tell you the story of my dad. He was an engineer since 1954, and he gets a call to his office. There was no cell phone by then. He was installing sewage line, and one trench collapsed, and many workers were buried under the failure. And he said, I'm rushing there, but it was like 1 hour away. And one of the backhoe excavator drivers had his brother in that trench, so he tried to save him by putting a rope around his waist and pulling him. And you don't want to do that, because this is my dad in 1955, and that's last year. He's my best friend. So why don't you want to do that? Because if you do the math for uplift resistance of 2 piles, which are your legs, you'll see that you actually need 10 times your weight. And this will kill you, really. That's why this is a case in Boston. Professional rescuers, they clear from a trench collapse the worker below the knees before they pull him out. These are equations that change our life. I will tell you about these 2 equations that changed my life. But I will also tell you that more engineering you put in life, more fun life is. So friction and equilibrium will bring more fun to your life. Now the serious stuff, case histories. I'm checking, I'm running out of time. So I have 5 cases to tell you about. Hopefully you're not bored. So let's start with the first one. Each one has an important message in it. I will start with the first 2 in Lebanon. So these are, you have 2 in Lebanon, 1 in Nigeria, and 2 in the US. I will try to cover all of them. This is a picture of Beirut, the city, the capital of Lebanon. You see the snow in the mountains, and the 2 projects are here. This is the Hilton one, the Trabo one. So the Hilton implosion was a project where a team had to demolish this building, and my job, my team, was to preserve the basements below that building so that the infrastructure around the tower do not show any dilapidation or do not break any pipes or cracks in nearby buildings. So it was the opposite of the demolition, a stabilization of the basements. Look at this tower, which was delayed in falling. So I was the first one to run to see what happened, because I was so scared that we're going to have problems. Again, Solj, we collected the soil during the design. But the biggest part, the most important one, the loads. What are the loads that we expect from the demolition to impact the ground and come back at us as a lateral push on the basements? How do you evaluate that? It's not in any book. And this is where I had to go back to the history and collect the time domain data from a nearby project that was demolished, similar but 2/3 of the size of the same building. So I had to multiply by extra 1.3 times, and I had to go back to the classroom and use the Fourier transform, discrete Fourier transform, to go from the time domain to the frequency domain and estimate what are the maximum accelerations expected in the vertical direction and lateral direction, to add it to the loads and use a pseudo-dynamic analysis. That was the best I could do. And I'm not going to go in details, but keep an eye on this curve, the calculated deformation or expected theoretical deformation of the walls of the basements. Of course, we had 2 rows of anchors designed here. I'm going a bit fast, I'm sorry, but I'll show you the fun part. So 3 drill rigs inside the basements, anchoring with high pressure grouting during installation prior to the demolition. And here we had to invent shock absorbents. I don't know how many of you did anchors. So you have the anchor plates of the active ground anchorage, and you have the conical wedges to lock the cable in place, and we had to add tubes welded at the top. In case the wedges gets loose, we remove the tube, we cut here, remove the tube, retension the anchor. So we keep the wall safe. These are some pictures during the explosion, and this is the best one, the final product when we saw the empty box, 12-meter deep, cleared for new construction. So when we measured with the inclinometer, these are during work, and this is after the implosion. The theoretical curve was that the wall will move inward, of course, because you remove the inside slabs. But the actual measurement showed that the wall moved towards the street. And because that tower that was delayed fell against the wall and pushed passively the top layers at exact location of the inclinometer, to tell you that whatever you plan for may not be the case that you expect. But as engineers, what can we say? I'm explaining here what happened with the tower, pushing, passive. So can we say that's a bad design? The answer is no, because you design for the worst case scenario. Here we got lucky. What can I say? And this is a new Hyatt Regency instead of the old Hilton. Like you were saying, taking a break between two cases. This is a picture of somebody standing in front of you, still alive, in Mount Lebanon. Yes, we have snow skiing in Lebanon. Many of you don't know that. Case 2. Deep excavation, Briaud towers. Here is a question. If you have an excavation between a new high-rise and an old house, which one you should worry about? The one with higher loads or the one with structural weaknesses? And here I'll show you a picture. I was hunting and I saw a failure of a rocky cliff with an antenna tower, and you see the two footings in the air. Because the truss is working as one solid piece, you know, you should think soil structure interaction. This is a real nice case for that. So you should worry more about the old house. Refer to the webinar on challenges in shoring. And this excavation, I'm jumping to show you this side was designed with 6 anchors. And when we reach 13 meters, the deformation obtained from WALAB, the theoretical one versus the measured one, was okay. But when we went deeper, and this is the location of the inclinometer, something went wrong. The prediction was the highest here, but already it was higher at the top level. And that called for looking what was the reason. The reason was the water source. Water is our #1 enemy. Flowing through this area, you can see the wetness in the shotcrete, and it created cracks and nearby structures in the adjacent building. And we immediately backfilled and called for another design with active strutting. And it really saved us. And this to show you the importance of monitoring every step of the way your work and comparing it to the measured data compared to the theoretical data, or what we call the observational method. Next case, let me see how we're doing with time. So between two cases, I show you a picture of where I come from, originally from Lebanon. By the way, this is the village where I originally come from. It's a beautiful Kadisha Valley that I encourage you to go visit. Maybe not these days with all the problems happening, but when it comes down. Next month, when peace is stable. Sea Breeze project is a project in Beaumont area, east of Texas. It's a wind farm where I was involved in designing the foundation for the wind turbines. Again, SolJ, we collected SPT, CPT data. Of course, I'm going fast. But to tell you, don't forget the steps. And then you collect the geometry, expected loads, I'm simplifying. And this from emergency braking, maximum moment expected. And then the question comes from the client, what foundation system should I use? You look at different problems, of course the wind forces, the mechanical braking, but also the problem of a surge wave on the shore of Beaumont. We expected some surge waves and we were worried about scour effect under the footing, so we automatically recommended deep foundations. But to analyze deep foundations under cyclic loading, you know, we teach you in class that you can actually add lateral load with vertical loads in the real case. You cannot do that because soil is not elastic. But why do we allow it? Because, and this for the students, because the lateral load affect the top layers, the vertical loads affect more the lower layers. That's why we're okay with that. Now, if you look at the theories for static loads, we have two theories, rigid theory, flexible theory that you taught us in class. And this one, L, the length of the pile is less than L0, which is the transfer length. And flexible theory is, well, L is larger than 3L0, and there has always been a missing link. And these are some design aspects. Maximum expected, usually Y0 at the top, 5 to 20 millimeters. How many degrees at the top allowed, especially for a wind turbine. And the maximum moment should be much less than the allowable structural moment of the pile. But in my PhD, I developed the analytical solution for a fourth degree differential equation. And these are some values of typical K value for the soil. And when you do that, the deformation lateral with respect to the depth of the pile and the time, so it's a dynamic solution. If you type it in font 16, the equation that we obtained was 33 meters long. And Ghassan is smiling because he helped me develop this equation. And here, on a deep excavation in Beirut, I made the workers hold the equation so they know and appreciate the work of the engineer telling them what to do, which is very few people do that. Yeah. So this is how it shows how the force is moving the pile left and right, here 18 millimeters, and the force is faster. And I will explain some more. At very slow frequency, if you have the solution for cyclic loading, the new theory should match the existing static theory because it's slow frequency, and it did. And we discovered the missing link. I'll show you a demonstration real quick. So if you look here, we have the pile diameter, the type of soil, and the length of the pile between L0 and 3L0. And you see that this is close to 3L0. That's why the new theory is matching, the red is matching the green static theory. But if you change that, the same equation will match the rigid theory. I'm going to skip. You have to trust me, but to show you quickly what do I mean. So the same pile in sand and mayonnaise will behave differently. This is flexible, this is rigid. And if you want to do the exercise, where is the fourth? You can simply use two different piles with your same finger. So if you put a straw, the straw will bend. But if you put a fork for the same finite element, because your fingers is a finite element model of the soil, and you push laterally, the pile behave, because a strong pile and the same soil behave rigid. Soil structure interaction, engineering in life. So the sea breeze, expected deformation, expected moments, this expected vertical settlements under maximum breaking loads. I would skip that and tell you it's getting ready to be built. It's been ongoing for like the past 5 years. Jaita caves from Beirut, so the next case. Marcelo is back or not yet? Because he visited last month. What time is it? 4 o'clock. I'll go fast. Am I good? So this is a case in Manhattan, New York, a case where the client was excavating in a busy neighborhood, but this building started tilting before they started excavating. First time, second time, a big third tilt, and the city of Manhattan stopped the works to say, guys, you don't know what you're doing. Third time on alert from the monitoring station, monitoring all these green dots, and you see the first burp, second, third, and then stop until I was called on site. So the question was, what is happening? Who's at fault? How to fix it? By analyzing the deformation, it was tilting and twisting a little bit. But if you look at the top here, 3.7, 3.8 inches at point P8, it went inward. A little bit less at this point. And the structural engineer was so worried that he felt the deformation is too much. So I tapped on the table. I said, you cannot feel. This is not a love story. This is engineering. Do the math. And settlement, he said settlement is continuous. He contacted the Manhattan DOB and they shut down the site. Long story short, I looked at his solution and he was putting struts from down here to stop the building, forgetting that the clients will go bankrupt if he does it. And the project will stop. What are you doing? And who told you that? If you do that, it's a good solution. I don't know if there is any structural engineer here, but sometimes you have to think. So sophisticated thinking. The settlement is at the bottom. So if this building is settling and you stop it at the top, you will break it in half. I said, of course, find another solution. And the client was there in the big room, big meeting, the geotech engineers there, the contractor, and they asked me, the question, what really happened? I said, just put together the reports. When you see site reports from the contractor, he submits it, it goes into a drawer, and then another report from the monitoring devices, they submit it, weekly report, it goes into another drawer. It should go in one drawer to one person who evaluates both things. And if you put it together, you will see that on that day, when there was a big jump in movement, they were doing secant piling. And then on this day, They were doing sheet piling with vibration. And on this day, they were doing down-the-hole hammering. So every time there is vibration on site near that building, there was settlement and deformation. I said, this is it. Stop what you're doing, change the methods. And the problem was over-designing. They over-designed the shoring system with huge piles, and they put secant piles where there was no water table. Why do you want to put secant pile when there is no water table? I became really crazy and said, what is the solution? I said, nothing. Change, make it lighter, make it easier, and stop drilling fast. Drill slowly and put the drilling tool inside the casing so you don't withdraw a lot of sand. And really the solution was just be careful, do nothing. And of course we did finite element analysis, matching process, reverse analysis. So you match the deformation that happened so you can predict what will come later after you excavate. So this is the matching process. And then you put the piles and tell them what will happen more if we do. So this is how we convince the DOB that, trust me, if we do it the way I'm telling you, it will not move more. The maximum damage already happened and occurred. And you do that with the theory, not with practice, because it's not feeling, it's both practice and theory, marriage between both. I will skip this to tell you that the maximum I calculated from 3.7 was 4.2. I said, maximum you're going to see fraction of an inch. Are you sure? I said, yes, we were monitoring anyways. And we kept going, and we were still within the norm. I will skip the structural modeling, but we had to do structural modeling to see so far what was the damage. But we reached the point where if you stay within allowable tensile strength and allowable compressive strength, the maximum we can allow this tower to lean like Pisa is 8 inches. I said, it's not feeling. You can make it lean double what it leaned so far and you are still safe within tolerable stresses. So don't worry. And we're not going to let it lean more than a fraction of an inch. And the project was nowadays is a beautiful tower. 455 Manhattan on West 19th Street. So this G-Law building, I get a phone call that we have a building in Nigeria, in Lagos, Nigeria, sinking 1 millimeter per day. So 1 millimeter is small, but per day. And it was finished, and it was inhabited, and the lawyer was so happy. The client was a lawyer, and that was his headquarters. And 1 week after, you start seeing small cracks. 2 weeks after, large cracks. And 3rd week, I get a phone call. And I said, first thing, start removing. Well, we did the analysis, of course, with the soil, geometry, finite element, but at the same time start removing all the water tanks, the AC units, even the chairs of the desk, everything, empty the whole building. And they said, why? Why should you do that? I said, because you are at the edge. You are at the failure. If you know, the load settlement curve, if you skip one little bit step and you stabilize the whole building. And they didn't understand this concept. And at the same time, there already was a team doing micropiles to stop the sinking. But they were doing micropiles and connecting them with long steel beams to the column. And that's not the way to do it, I said, because by the time the load comes here into the bending deflection of the beam, down to transfer the load to the micropiles, already this sunk 20 millimeter. you have to do something different. So we called for activating the micropiles by putting a jack. So when you install the pile, the micropile, first bring it as close to the column as possible, and then activate it, means make the micropile fail, not the building. So put as much load as you can since the pile is there, and make it sink. And that's the operation you see here. You know, when it's on paper, I'm putting the video next to the theory and practice. You see the difference. And that's the way we were able to stop by adding, I don't know if you can see here. So the original design was about 200 piles, and we had to add the piles in green to stop. And this is a recommendation to have an extra safety. So this is one pile, and this is all the piles, about 200. So put together, why am I putting this? That nobody knew except after we stabilized the building, and I discovered back to the problem. So if I went back to the communication between the structural engineer giving the numbers of loads to the design build contractor doing the micropiles. And there was a factor of 10. One guy gave the number in kilonewton, and the other guy took it in tons. So what is safety factor of 3? Not important anymore. You have a factor of 10. This is true real life. Don't ever go with an answer without units, or if you get a number, always check the units. Make sure it's even correct the architect. Make sure, like, do the approximate area method. Make sure the column the load is giving you is approximately okay. So for 40 feet by 20 feet times 1 ton per square meter, or a tenth of that. So you get approximate answers. So, and this is very important. We were discussing this today at the table at lunch. Geotech, structure, architecture, all the engineers must communicate before launching the project. Make sure you collect all the data before you give any answer. I'm getting close to the end. I hope you're not bored. Business as engineers, this is more fun. Make money, but be careful. So I like all of you to be in this top part, have this motivation to make things happen. I'm sure none of you is here to be in this room. I'm sure you're not here, I'm sure. Be careful with temperature. This is a world map. So if you are studying here, you want to work here, it's too hot, or in permafrost area, be prepared to be international with the temperature map, but also the corruption map. So if you're okay in the orange, you can easily work in Canada. Maybe more difficult to work in Nigeria, but actually in red and very dark red is where you make the most money. If you are smart. So be ready to work internationally. Last chapter. This is a picture from the area called Zaytuna Bay in Beirut, and Phoenicia Hotel is where we are planning. I'm helping the Lebanese Geotechnical Engineering Society to plan their first Pan-Mediterranean conference, if Lebanon still exists, in 2025. So it's a nice, fun country. Please be there. Lessons learned, my final slide. If you want to take a picture, go ahead. So lessons learned, collect the data, of course, SOLGE, all the data, SOL, geometry, load, and never ever give an answer without units. Don't rely on intuition. Always marry theory to practice by all possible methods and all available data. Simplify to get the first estimate. In summary, do the sophisticated thinking prior to the sophisticated analyses. Don't limit yourself to the code. You know, I've heard engineers say the code says this, the code says that. The codes are not made to solve every problem you meet. Your brain is. Innovate if needed, of course, without ever compromising safety. Conduct monitoring, value engineering, and long-term observation, or what we call the observational method, is my favorite as a design-build person. It's your best continuing education. Be ready to expand internationally, especially by staying connected to ISSMGE. I love this quote by Steve Jobs before he departed. I think he was giving a speech at Stanford graduation. The only way to do great work is to love what you do. And I think I have one equation, last equation to give you. To understand soil better, you have to dig deep. To understand love better, you have to dig deep also. So, soil equal love. Thank you very much.
You brought about a very important topic that I certainly support wholeheartedly, you know, the use of theory and practice and the use of data. And I'm sure that Professor Buchanan would be also very supportive. So we appreciate your thoughts and your ideas and the fun as well. So I have a plaque for you.
Oh.
For the, it says, Texas A&M University recognized Dr. Marc Ballouz for presenting the 31st Buchanan Lecture entitled Geotechnical Engineering, Marriage Between Theory and Practice.
Thank you so much.
Thank you.
May I ask
And
Marc to join us?
yeah, we'll do that in a minute.